Alright, so let's get started on Chapter 3. Chapter 3, 1, we're going to do exponential functions and their graphs. And so exponential functions starting to get a new type of graph that we haven't really dealt with before. Alright, so far we've dealt with algebraic functions, so polynomials, rationals, x squared, x cubed, things like that. And now we're going to get into exponential and logarithmic functions. And so the difference now is that our x's aren't going to be down in the base, they're going to be here in the exponent. Alright, so we're dealing with exponential variables. And so how do we deal with that? How do we change things? Things like that. And so functions like these are called transcendental functions. Alright, so don't really need to know where that comes from. That's just the title for this, just like quadratic is the name for parabolas, things like that. So transcendentals are dealing with these exponent and logarithmic type functions. Alright, so let's take a look at the first one. First thing that you got to be able to do is just plug this into the calculator. So first one's very straightforward. What is 2 to the negative 3.1? What is 2 to the negative pi? What is 0.6 to the 3 halves? Right? So shown here is how you would punch this into the calculator. I think a lot of you know how to do this already. Make sure here that we're using parentheses if we're doing fractions. And so these are the numbers that you would get. Right? So make sure you can do that for 0.9 to the 1.4. Plug it into your calculator, see what the number is, and then check the back of the book, make sure you're getting the answer there. Just to make sure that you're okay with dealing with exponents on your calculator. If this isn't working for you, we might have to check the settings on your calculator. So just kind of a test to make sure that your exponents are working okay on your calculator. Alright, example 2. Let's see what the graph of exponential functions look like. They're going to be like this. They're going to be starting low, and then boom, taking off as we get up like this. Right? The reason why this is that 4 to the, if this becomes a really big number, it gets really, really big. 4 to the, if it's a fraction though, 4 to the, negative, it turns into a fraction. If we remember what negative exponents do, they turn us into fractions. So when we go negative, we're going to be really, really low, and positive, we're going to get really, really big. Alright? So what you need to do here for 1/2 to the x, make yourself a little table like this and fill in the y values and then do a quick sketch of what 1/2 to the x is going to look like. Alright, if you're ready to go, we're going to move on to 3, and 3 is the same thing but for negatives. And remember what negatives do. Negatives turn our problem into a fraction. So 2 to the negative x is really the same thing as 1. Oh, sorry, the pen's not working there. Turn this on. So 2 to the negative x is the same as saying 1 over 2 to the x. Okay, so as our x's get big, the fraction gets really big, but the number becomes really, really small, as we see here. The bigger the number gets, the smaller the y value turns into. And so we'll have a coming in for a landing type graph, as opposed to back here in example 2 where we were taking off as we moved left to right. Alright, so see if you, missing the example in there. So let me pause this and bring that up for you. Alright, there we go. So 6 to the negative x is what you need to try to sketch. So I would recommend starting with a table, a couple numbers, maybe -3 to +3 for your x's, get some y values, and then plot those, see what the graph does. It should come in for a landing if you're doing it right. Alright, so let's introduce solving some of these exponent problems algebraically. And so we're going to introduce the one-to-one property. What the one-to-one property says that if you have the same base, 3 and 3, you get to cancel them out and you're left with just the exponents. Alright, so in this problem, 9 and 3 don't match up, but you can turn 9 into 3 squared. And at that point, 3 and 3, we're going to cancel them, so 2 equals x plus 1. Minus 1 to both sides, so x equals 1. You can see the same thing going on here, 1/2 to the x, and 8. Okay, no match yet, but 1/2 to the x can be turned into 2 to the negative x, right? Flipped over, negative x means flip over to a fraction, and 8 is the same as 2 cubed, so we can cancel our 2's out, and we've got x equals -3. Alright, so see if you can figure out what to do with 51. See if you can get the same base, cancel them, and then solve for x. All right, so now we're going to look at transformations. We've done this before. You guys know how to do this. It works just the same way when the x is in the exponent. X plus 1, just the same thing as before. We're going to shift this 1 unit to the left. Minus 2 out here by itself, 2 units down. Negative out in front, flip it over the x-axis, flip it vertically. Negative in with the x, we're going to flip it horizontally. We're going to flip it side to side. All right? See if you can figure out what the shift is of 3 to the x plus 1. All right, so now we've got this thing called the natural base e. All right? And so the natural base e is a useful thing for a lot of real-world applications, for growth and things like that. A lot of real-world situations will follow patterns dictated by this. I don't know if you ever have seen, there was a documentary about like beauty and models' faces all had ratios, like the distance from their nose to their chin and the distance from the chin to the top of their face. The ratio followed a pattern that was based on this natural base thing. So it shows up a lot in nature. We're going to use it from time to time, and anytime you see e, it is a number. It's like pi. Pi is 3.14159. E is 2.71828. Right? Goes on forever. It's an irrational number. We're not going to try to remember all the numbers. We just know that e is this base. All right? You need to be able to plug it into your calculator. E to the -2, e to the -1. All right? See if you can plug it in with 3/4, e to the -3/4. That's your job. Check the back of the book. Make sure you get the right answer for 33. All right? Okay, so now we need to be able to sketch the graph of each natural exponential function. So 2 to the e of 0.24x. And let me just grab the graphing calculator and I'll put up what the graphs should look like. So y equals, let's go find e. It's down here right above the natural log. So second ln. Get e to the, oops, sorry, I forgot the 2 in front of it. 2e to the 0.24x. Close our brackets. Let me check my window. Seems pretty good. Let me go ahead and graph this. It starts low, and boom, it starts to take off. What's anything to the 0 power? The answer is 1. So right here, we should be crossing at 2. 2 times 1. All right? And so we can do the same thing for this one over here. And if you have a negative up here, what's the graph going to look like? Think about that as I type it in. 0.5 e to the -0.58x. Did you say it was going to come down for a landing? Good job if you remembered that the negatives drop and decrease as we move left to right. All right, so your job now, oh, there they are on here. Your job, get 41 to work on your graphing calculator, sketch out what it looks like. All right, last two real-world situations. Compound interest follows a formula here, and compounding continuous interest follows this. So what happens here, if you go to the bank and they give you, or you give them your money, the reason you do that is because they're going to give you interest. So sometimes you're going to get interest at set points in the year. So the amount that you get at the end is based on the principal, the amount you give them to begin with, times 1 plus the interest rate. This is going to be in a decimal. So 5%, you're going to write 0.05 over n. N is how often you get interest, times nt. T is how many years you're going to be getting interest for. Now, some banks give you continuous compounding. That means that you're getting interest all the time. It's not like every month or every week. It's just constantly you're getting interest, a little bit all the time. And that follows this formula. P to the e, natural base, times r, whatever your rate is, times t, however many years you're going. All right, so let's look at this problem. A total of $12,000. So right away we know that the P is 12,000. Is invested at an annual interest rate of 9%. So our our rate is 0.09. Find the balance after 5 years. So our T is 5. If it is compounded, so A quarterly. So our amount is going to be 12,000. 1 plus 0.09 over quarterly. How often do we get this? Quarterly means 4 times a year. All right, and so then we have 4 here times 5 years. Over the course of 5 years, we're going to get 20 interest payments. All right, so let's plug that in real quick, see what we get. 12,000 times 1 plus, parentheses again, 0.09 divided by 4, and that's going to get raised to the power of 20. And so our $12,000 will have grown to almost $19,000, $18,726 after our 5 years. All right, so we could do the same thing with the monthly. 12 would be our n, and then continuously, we would just plug it in here. All right? Go ahead and see what you would get for 59. Try it with the same thing. All right, last one. So now we've got a half-life problem. So this is, if you do chemistry, some physics problems talk about half-life, which is the amount of time that it takes for something to decay half of its original amount. So after 1599 years, half of the original amount of radium will remain. You go another 1599 years, you're going to have a quarter of the original, and then an eighth, and then a 16th, right? So let Y represent the mass in grams of the quantity of radium. The quantity present after T years is given by this formula here. You're going to be given the formula. We need to do stuff with it. So what is the initial mass when T equals 0? So let's just plug it in and find out. Y equals 25 1/2 0 over 1599. Let's look at the different parts here. All right, so this is a constant. That's always going to be a half because it's a half-life. This is time, and this is the actual half-life of a specific compound. All right, so 0 divided by 1599 is 0. What's anything to the 0 power? If you said 1, nice job. So the answer to A should be 25. All right? And then the second thing we could plug into our calculator, instead of 0 here, we would change it to 2500. So let's see what we get. 25 times 0.5 to the, in parentheses, 2500 over 1599. If you get your parentheses right, you're going to get the problems right. 8, okay? So how much of the initial amount is left? We started with 25, and now 8.4 is left over. All right? All right, so try 1 on 73. That's it for this section. Any questions? We'll go over it in class.